So, let us prove an important result in linear algebra, which is the unique representation theorem. So, I will state the theorem. Let S be a vector space and T be a subset of this vector space and non-empty. This set T is linearly independent if and only if, I mean there is a forward statement as well as a reverse statement, if and only if for each non-zero x belonging to the span of this space T, there is exactly one finite subset of T denoted by P1, this collection of vectors P1, P2 so on till P suffix n, and a unique set of scalars C1, C2 so on till Cn, such that x can be written as a linear combination of all these vectors P1 to Pn through the scalars C1 through Cn. So, before we begin, we have to understand what we need to prove. So, there is a forward statement which says linear independence should imply unique representation, and then there is a reverse statement which says if it is unique representation then it is linearly independent, and that is this if and only if statement. So, let us try to prove both these parts. So, to prove this part, we shall establish this by contradiction. Let T be a linearly independent set let us assume that there exists x is a non-zero vector belonging to the span of T whose representation is not unique, and this is where we have to establish this result. Thus, there exists two subsets of T, namely a set P which is comprising of vectors P1, P2 so on till P suffix m, the PIs span T, Q having Q1, Q2, so on, Q suffix n, the QIs span T, see the difference between M and N here, such that X can be written in two forms, one using the set P and other using set Q. So, X is basically a linear combination of vectors from the set P, and we said that this representation is not unique. So, therefore, you are using another combination using vectors Qi and associated scalars d sub I, where I think I have to make a point here, Ci's and di's are non-zero. Now, let us rearrange the terms in the representation of X, that is whatever we have written down here. So, let us rearrange the terms in the representation for X. So, what we get is sigma I equals 1 to m C sub I P I minus summation I going from 1 to n d suffix I q suffix I, this is basically the 0 vector. Now, as PIs and QIs belong to T, right. If P intersection Q is a null set, then PIs and QIs are different. So, this contradicts the fact that T is a linearly independent set as their non-trivial linear combination cannot sum to 0. Hence, there must be some overlap between the two sets, right. As QIs and PIs belong to T, if the intersection of P and Q is a null set, then PIs and QIs are different. This contradicts the fact that T is a linearly independent set, as their non-trivial combination cannot sum to 0. So, therefore, there must be some overlap between these sets. So, let us proceed further. Let m be less than n, right, because there is some overlap, and let m be less than n without loss of generality. Now, I call this equation before equation 2, and possibly the first equation that we have in the theorem, we can just call this equation 1. Okay. So, equation 2 holds only if for every p suffix I there exists some q suffix j such that p suffix I equals q suffix j and ci minus dj vanishes. This is true as only trivial linear combination of vectors in T can be 0. Okay. Now, renumbering the elements, in Q we obtain, say, p suffix I is q suffix I, we can just label this, and then Ci is a scalar, Ci equals di. Thus, the set P is part of the set Q. Let us just call this this equality here as equation 3. So, from 2 and 3 we will end up with summation I going from m plus 1 to n di q suffix I is basically this 0 vector. Okay. So, let us call this equation number 4. So, as if Qi's are non-zero, they should be linearly independent, and di are non-zero. So, therefore, the only possible solution is Qi being this 0 vector. So, therefore, if we neglect the 0 vector, we define the set Q is basically Q1 so on till Qm, which is basically this set P which we arrived at, because Pi equals Qi for I equals 1 to m, and therefore, the representation is unique. So, let us get to the other part, which is if we have a unique representation, does it imply linear independence? So, again we shall establish this through contradiction. Let every vector x belonging to span of this set T have a unique representation in terms of vectors in the set T comprising of say T 1 to some T k. Let us assume that T is a linearly dependent set, then there exists A 1, A 2 so on till A k, where at least one A I is non-zero such that this linear combination is a 0 vector. Let A 1 be non-zero, consider, I will call this equation 5, consider x which is equal to T 1 say suppose, and this is given by minus 1 upon A 1 summation I equals 2 to k A I T I. Now, as x does not have a unique representation, this implies a contradiction because we assume that it has a unique representation. So, therefore, T is a linearly independent set, and this completes the proof of this theorem. We will stop here.